So as we have indicated earlier, that we have moved the decision of the branch to an earlier stage, and we have now at this stage instead of this stage by just having this new comparator hardware at this particular place. When we have it at this particular place, then just after this, we already knew what is the outcome of the branch. We already knew if it is, for instance, equal or not, if we were to use branch equal. Also, we have mentioned because of this, we have to wait at least one stall after the branch. When I had it here, we had to stall for three times. But after we moved the comparator at this stage, so that basically tells us that we have to stall for at least one time. And because of that, if, for instance, I switched the branch equal, the very next instruction afterward will just be stall, meaning bubbles or not, which is no operation. And if we assume that the branch is taken, the very first instruction after the stall, it would be actually the target branch address. Branch is taken means, for instance, whatever I am trying to compromise or whatever I would like to check is true. So for instance, if I'm saying branch equal this, equal to that or not, it is true. Or if I said branch not equal, then they are not equal, so it is true, not equal. So whatever I'm checking, it is true. And in that sense, meaning that it is taken. As an example, if I have something like that and it is taken, I would go to that particular address. When I will go to that particular address, we'll find that particular instruction for instance. So the bottom line that now, at least after the branch, I have to wait for one stall. Okay, so what happened if anything's before the branch? We mentioned that after the branch, we have to stall for at least one time. But can we have data hazards before branches? Let's see what would be the case with this example. Add these two registers, whatever inside these two registers, and put the results in register number 1. In the normal case, register number 1 will be updated at this particular stage. If I have the forwarding, register number 1 is basically available after the execution here. And then again, add 5 register, whatever in register 5 with whatever in register 6, and then update the register number 4. So normally register 4 will be updated here. However, as we mentioned, the earliest available of register number 4 would be at this stage, because basically I am feeding the execution here, or the ALU, with register number 6 and the register number 5, and then add. So this is basically will be add. So whatever is here is what should be written in register number 4. So that means that I already knew that the information is ready at this particular stage. Assume that I have here the branch equal 1, 4, certain address target. Again, as we mentioned, now we are doing the comparison at this particular stage. Unfortunately, it is available here, and I need it here. I can't go back. And because of that, I have to add stalls or bubbles. And then the branch will be afterwards. Now the branch needs the information here. It is available here, so I can easily be forwarded to that particular place without any problem. But I have to be waiting at least one time in this case. Please remember that if no forwarding is not available, I have to wait all the way till here. That means that I need, unfortunately, to have another stall, and then my ID stage will be here. I will write here, I will check here. That means that I need to stall for one more time. Also, I would like to highlight that earlier, as we have mentioned, that we can check, or what we supposed to know, the output of the branch is just after that. If this was the case, actually having it here at this moment should be okay, because it is ready here. I need it here, so that should be okay if this was the case. However, from now on, in all of the branches, by default, we will assume that actually is it checking the branch outcome at this stage, unless otherwise specified. Unless otherwise specified. So by default, we will assume that this basically the architecture that I am implementing. Let's take another example. Suppose that I'm doing a load word. Basically, with this load, add a certain particular address to that particular register. So that particular register will be updated here, but it will be, of course, available after this particular moment. Add this to this, update 4. Again, it will be updated here, but it will be available at this moment. Unfortunately, if I have the branch here, again, I need to compare at this particular stage, but unfortunately, it is available here, so I can't go back. That's why I have to stall for one time, as we mentioned in this case. Then I can forward it from here, and it is already available here. I can take it, or I can forward it from the memory. Let's take that example. Suppose that I have a load word, and then after the load word, I have directly a branch equal this one, 1, 0, and then target. So I would like to check if whatever in register 1 is equal to 0 or not. Again, I would like to check here. Unfortunately, with this load word, the data is available after this stage. Again, I can't go back. So I have to stall for one time. Then the ID is here. Again, I can't go back. So that's why I have to stall for another time. And then at this particular stage, I can easily forward my output to my comparator here. But I had, as we mentioned, to get 2 stalls, as we have seen. So just to recap, whatever we had earlier with the branch, we have to check it like to know the results after the memory stage. But we have decided to have it earlier in order to install the number to reduce the number of stalls after the branch. Earlier, when we had it at the very end after the memory stage, if you recall, we had actually after the branch, each time I have to stall for at least 3 times. Having it at the comparator stage, at least we have to stall for 1 time. So no matter what would be the case, I have to stall for 1 time. The question is, can we do better? Can we have a better implementation that will enhance the performance and increase the throughput? Or in another sense, can I make it in a way that I don't have to wait for 1 stall each time? The idea came as a prediction algorithm. Let's try to think as a prediction algorithm, meaning that I need to predict in advance what would be my results. Okay, so then that's fine. But if my prediction was not correct, then what I should do in this particular case? They said that try to predict something. If your prediction was correct, then you are saving 1 stall. If your prediction was not correct, then you have to stall for 1 time, because you will know a little bit later that actually this prediction was not correct. And what you need to do is just flush whatever you had and then fetch a new instruction, which will end up stalling for only 1 time. So the worst case scenario in this case is to have it as whatever you have in the best case scenario in the previous case, which is 1 stall. But the idea is, what would be basically the motivation or the algorithm of prediction? How we can do that, and so on and so forth. This is what we will talk about shortly. So here it says like, okay, let's assume that the predict is not taken. And then I would assume that it is not taken. So I will just fetch that particular instruction and then go inside my pipeline. I would know later that actually my prediction was correct, and then I will leave it. I didn't need to do installs, and that's why I'm benefiting. In another case that actually I have predicted, as an example, to get this one, unfortunately, throughout the pipeline, I discovered at this stage or later or whatever that actually my prediction was not correct. When I have tried to see if this is equal to that or not, I found that they are actually equal, and I have to go to that particular target address. That's why what I need to do is just flush everything that I have already fed into my pipeline, flush it, and then take a new correct instruction in this case. What would be whatever I'm losing, or what would be the worst case scenario that I'm losing, is just one stall. But this is, we already knew from the very beginning that this is at least what we need to stall after the branch, correct? What I need to stall after the branch is one time. So here, either I will benefit or I will just go as the normal case. Okay, so again, here, the same exactly. After that, I would assume that I will take a certain particular instruction, but unfortunately, it was not correct. So then I will flush, add bubbles, and then fetch the correct instruction in this particular case, and then move forward without any problem. So what are the options of my prediction? There are actually a couple of options here. There is static prediction and there is dynamic prediction. What does that exactly refer to? Static predictions means it is fixed. I will just decide from the very beginning what I should do. So I will say from the very beginning, as an example, I will take the branch as taken. My decision is fixed from the very beginning. I will take the branch as taken. And then I will just go through my code. I have assumed that the branch is taken. So the very first branch that I will face, I will assume it is taken. So that means that the next instruction to be fetched is the target address. Correct? I will fetch that instead of the next one in the sequence. I will fetch that and then go through the pipeline. And then I will see if my prediction was not correct or not. If it is correct, that would be fine and benefit like saving this one stall. If it was not correct, I will just flush it and take the correct sequence. And then go through my codes, go to the next branch. I have already decided from the very beginning, it is fixed, that I will assume that all the branches basically were taken. No matter what I have faced. No matter if I assume, as an example, the worst case scenario, that all the branches would be opposite to my prediction. Meaning that I have assumed from the very beginning that all the branches have to be taken. But I found actually through my code that all the branches, it's exactly the other way around. It's exactly opposite. So I will not change my mind because I have decided from the very beginning that I have only one decision. It is fixed, it is static. Or I may say it would be not taken. Or I may say from the very beginning, it would be in one direction taken, in another direction not taken. So if my target address is, as an example, forward, I would assume that this is taken. If my target address is reverse, then I will assume that it is not taken. The basics, my decision is not changing with whatever I'm facing. I have just at the very beginning one decision, fixed decision. And then no matter what I am facing in my code, it will not be changed. Okay, so that's fine. But unfortunately, with this scenario, as I mentioned, you might have actually all the predictions to go opposite to whatever you had, and then you are just losing. But remember something, that even with the worst case scenario with this algorithm, the worst case scenario, it would give me the same performance as the normal case. So if it is not benefits, it will give me the same. So of course, I would choose something like that over non-prediction algorithm. Then they have decided later on, okay, so why not to do my prediction dynamically change? What does that exactly mean? Meaning that I will choose at the very beginning something, one of the ways, and then according to my experience in that particular code with the branch, I will begin to change my decision. For instance, I would say that the branch is taken. So my branches, I assume that all the branches is taken, meaning that it is true. Branch equal, it is true. So always my next instruction is the target address. And then while I'm going through my code, I found the branch. I took that branch. Then the next instruction to be executed as actually the target address. So I fetched that target address. And then I fed it into my pipeline. Assumed that I found that my prediction was not correct. Assume that this is the case. I might say, okay, so now I dynamically change. Then I will change my mind with my next experience. Because in that one, I had the experience that my prediction was not correct. So why not to change it with the next time? Then I will go with the next time. I have it changed it now from taken to not taken. So while I'm going through my codes, I will go to the next branch. But remember that I have it changed my mind right now that not taken, meaning that the next instruction to be executed, I will just fetch it in the sequence. I will fetch that. Then in the pipeline, I found that actually my prediction was correct. So I will stay as I already chose in the previous things. Let's say that now I'm still under the not taken. I will go to another branch, took it. I found that my prediction was not correct. Then I will flip. And this is what they refer to as an example with trivial algorithm of prediction, or let's say like non-mature prediction algorithms. So we will go over this in details. We'll see like a little bit of more mature algorithm. But before we go that deep, let's try to highlight some important issues here. So with this dynamic branch prediction, I can have, for instance, a branch prediction buffer because I need to see what my history was. So in this branch history table, I have, of course, to save whatever is happening and so on. And then I will get a prediction bit. And this prediction bit might say that, hey, either taken or not taken according to the history. If the prediction is wrong, then again, as we mentioned, flush the incorrect instruction in the pipeline, and then restart the pipeline with the right instruction as we have mentioned so far. But also we can add what we refer to as branch target buffer, because whatever we have explained in the previous slides at the prediction bits, it just decide when a branch is taken, but it doesn't tell where exactly it's taken to. Having a branch target buffer, it actually will save exactly where the branch should be taken. And at the same time, I can also take the next instruction in the sequence. So in that sense, I'm actually taking both of them with me. So if I have discovered later on that I was wrong, then it is easy that I have already in my pipeline the other one without losing much more time and so on and so forth. But of course, in that scenario, we need to read port instruction memory because actually I have to read both of them. So back to the prediction algorithm, there is one prediction, what we called 1-bit prediction accuracy, because I'm just flipping with just one unsatisfied or non-correct prediction. Let's say that I will assume that bit equal to 0 or state equal to 0, indicating branch not taken. And the one actually is the other way around. Let's go over this in details now. So this is 1-bit prediction. Assume that state 0 or bit 0 is branch not taken, and we will refer that as NT, and one branch taken, and we will refer to that as T. And then we'll have my two states here, 0 and the state 1. And suppose that we began with state 0. Suppose that my first state is state 0 in my state machine. I have my code, meaning that while I'm searching for a branch, for instance, with my first branch, I am in this state, so I will decide that it is not taken. Okay, so that's fine. If this is the case, let's assume right now that I have, for instance, add whatever, subtract whatever, and then branch equal, and then multiply, load word, and then again branch equal, and so on, so on, so on, so on, and then again branch equal, and see like how we will deal with these such scenarios. The very first things, as we mentioned, we are in this. So I'm assuming I am not taking. So I will go in my code, and then I will see here this branch equal. I am assumed that it is not taken. Not taken means what? That I'm not going to that target address, and my next instruction to be executed is that one. So I will fetch that in my pipeline. And then in my pipeline, I will check if my prediction is not correct or not. They are equal or not equal. I'm assuming that it is not taken, so it's not equal. Later on, I found that my prediction was correct. That means that I will stay in the same state, meaning that I have a not taken situation. I am still in my same state, meaning that while I'm going after that to the next branch, I am still in the not taken state, meaning that when I will go to that branch, I will fetch this instruction afterwards at the next instruction to be executed. Suppose that later on here, I found, unfortunately, that my prediction was not correct. So what I would do, flush this, go to that particular address and fetch it. But now I was under the not taken, but taken come. So if I was at the not taken and the taken come, interestingly, I will move to the next state, which is 1. So after that guy, now I have decided to be taken, as you can see from here, because I went from bit 0 or state 0 to state 1. So I am under the decision of taken right now. So any subsequent branch, when I will face, I will decide in advance that it is taken. Taken means the next instruction after the branch is simply the branch target. So I will go here. I will assume that the next instruction is the target. So I will fetch that instruction. And then again in the pipeline, assume later on I found that my prediction was correct. So I am still under the taken. So that means I was under the taken. I faced a taken branch. So I'm still under my same scenario. So now, as we mentioned, we are under the taken right now. I'm going here. So taken means I will fetch that target address at the next instruction. Later on, unfortunately, in my pipeline, I found that I was not correct. And unfortunately, it should be not taken. What I would do afterward, I will just go to the state machine. If it is not taken, this means that I will move to the next state, which is 0. Then anything afterwards in this situation, it will be not taken, and so on and so forth. So as you can see from here, that my algorithm is as simple as changing my decision with just one experience that is opposed to whatever my prediction, I just flip. So what would be the case, for instance, if I have a ping pong scenario? What is a ping pong scenario? Meaning that the correct prediction that I should have followed is actually opposite to whatever I am already predict. Meaning I am going as a not taken, but I found taken. So I will flip to taken, and then it is not correct. So then I will flip to not taken, and then it is not correct, because actually the branch by itself is going the other way around. So this is what we call the ping pong scenario. In this particular case, meaning that I will go with all my prediction not correct, and that means I will have one stall for all of my branches in this situation. Nevertheless, this is actually the normal scenario. So I didn't lose more than the normal scenario. I might benefit, but I will not lose. But interestingly, whatever with this unmature, if you will, or where you refer to in this particular situation, that to predict with just one bit, this is very close to whatever the experience that we all had in the early childhood. Let's remind each other with what happened in the early childhood. In the early childhood, when we had an interface with anyone, suppose that you went to the park and went to play with other children in the park. With just one very good interaction, when you return to your family, what you usually said is, I have a BFF. Correct? I have a BFF with just one interaction, because you are not mature yet. You just have a one-bit prediction. Interestingly, if you went again to play but that same person give you a hard time, that same exact person, and you are the exact same person, you return to your family, or you might say to that person, you are not my friend anymore. So you just flip the decision with just one interaction because you are not mature. But interestingly, when your age become a little bit older and you become more mature, you are not that actually very fast decision maker. You need to wait a little bit. And remember that this actually happened interestingly with the growing of your age. Maybe later on you have like this after 2 interactions, maybe later on after 3 interactions, and so on and so forth. When you are mature and you have for a long time a good interaction with someone, then if that same exact one have a bad things to you, you will not just flip. You might say like, he had stress, he had a bad mood, he whatever, any things happened bad to the family and so on. Usually give excuses, correct? It's happened again, you give excuses and so on. You will not flip unless you are sure that that person already changed. It's exactly the same. Here we have explained with just one bit prediction, but there are other algorithms that we will go over it with a little bit with more mature state machine, if you will, that would not change momentarily with just one flipping decision with whatever your prediction.